Hello and welcome to the next edition, the latest edition of Straw Building UK's lunchtime webinars. Today, we are pleased and honoured to have Annie Benton talking to us about Ecococon and more specifically looking at the data provided from her own property. So, let's go on to the next one. Let's go back. Who is SBUK? SBUK is Straw Building UK. We are a straw building association. We comprise of advocates of straw building, bio-based building, educators, builders, and manufacturers. We have and have done over the past decade been working on several aspects and several tools that have enabled us to really lead the way when it comes to building with straw. If you go to our website, you can see some of these. They are available free for you to download, one of which is the Straw EPD. That was one of our previous talks. Also the technical guide and also the Straw BIM. So, who is Annie Benton? So, as you can see here, Annie Benton is a Straw Building UK board member. Specifically, she is our treasurer, and she is also a certified passive house designer and technical specification officer for Ecological Building Systems, an organisation based in the UK. They offer natural products in the built environment, from airtight and windtight systems, ventilation and extraction, insulation, and as well as that, they also often offer training courses too. So as well as this, Annie is a director for Edita, I hope I pronounced that correctly, a company that specialises in hempcrete. And I think, Annie, what I'm going to do, without further ado, is go on to the next screen and hand over the controls to your good self. Over to you, Annie.
Thank you. Hi, everybody. So, as Cyprian said, I have an interest in natural building and sustainable construction, and I sit on the board for SBUK, but I also do technical advice for ecological building systems. You may or may not have heard of them. As Cyprian says, there's a wide variety of products that we supply, but we do an awful lot of technical advice and guidance, as well as support on site and a lot of educational awareness and training as well. I've just recently finished my master's at CAT in green building and received a distinction, and my dissertation is effectively the topic of this webinar. In my past life, I actually worked in neuroscience research in London before becoming a secondary science teacher. So my background comes from a science perspective, but also an education perspective. And now it falls into doing practical stuff on site and all sorts of nice, fun things. But it sort of aligns, the science stuff aligns with me. I also just want to apologise if my dogs bark, and also the sun is shining, which means we're generating a lot of electricity, so I have got everything on in the kitchen. So if you hear noises and beeping, it's probably appliances, so apologies for that. So I thought I'd just sort of start with some figures. In terms of when I did my dissertation, obviously there's a lot of literature you're reading about all sorts of things to do with construction, and so these figures are highlighted from a lot of reading, and I don't know if you know what they are associated with, but I'll take you through them. So the global construction industry is responsible for approximately 39% of carbon emissions globally, which is a huge amount. That's operational and in construction and in build. In the UK, the construction industry is responsible for about 49% of the UK carbon emissions, which is enormous. On top of carbon, the global construction industry is also responsible for between 40 and 48% of the global energy consumption as well, which is just a profoundly huge figure. And 41% of total end-use energy consumption in the UK was used to heat water and space heating in residential domestic buildings, which is enormous. They've taken transport out of the initial energy calculation, but still, with the focus here on the need for space heating, which ties into more of my dissertation. Additional sort of data that I sort of dug around and found was that residential buildings in the UK are also responsible for 23% of total end greenhouse gas emissions, with 13% them associated with space heating, and mostly because the buildings that we have are incredibly inefficient. Most of them are graded at a really poor level of EPC, and we have a big job to do. So you may be familiar with these figures and stats. If anybody wants a copy of my dissertation or they'd like to read it, all the references are in there. You're very welcome to it. Just maybe email us through SBUK, or you can contact me directly. I'll put my email back at the end. So we've got this big issue where the industry is using too much, we're producing too much waste, we're using too many resources. But on top of that, we also have a huge performance gap relevant to design and in-life experience and energy use of a building. So we are still building buildings that we know will not perform the way that they should, yet we still do it. And for an industry that is very resource heavy and carbon emission heavy, we should be building buildings that we know are going to perform. So I think, so this is sort of where the dissertation sort of came from. The IPCC release reports. I don't know if you've not heard of them, the Intergovernmental Panel on Climate Change. They release reports. And the one they released in 23 restated the involvement of human activities causing the global warming of the Earth. We can see that there's huge impacts everywhere, from extreme weather patterns, global food and water scarcity, disease, mass migration. We're going to see more of these impacts locally to us now in communities, including things like more overheating in buildings and that sort of thing. So we're all massively impacted by it. But the report also highlighted that if appropriate reductions were made across multiple systems and industries, actually we could slow it down within 20 years. And construction was mentioned in there as an industry. So what are we doing? Are we acting quick enough? In my opinion, no, we're not. But the fact that there is strategies and things out there that we could be doing, I think is really positive. And I think as an industry, we need to wake up and get on with it. We have a lot of the solutions already. So what I'm going to chat to you today is about my dissertation in terms of what I did and the data collected about our Ecococon family home. But I'm going to give you a little bit of context first. So this is my actual parents' home as a self-build. I came in later when sadly my dad got diagnosed with cancer and we rallied the troops. So it was their story to tell and their journey to tell. But because he's not here, I'm going to tell it as best I can. So in the beginning, my parents, effectively, they bought some land here in Suffolk with planning permission for a building that was not a sensible building, not energy efficient, facing the wrong way. Yeah, not insulated properly, etc. So they re-put the planning in and it got granted for a sustainable home. And they spent a lot of time trying to work out what materials to use. And my dad was a real energy fanatic, passionate about the climate, passionate about the environment, passionate about the physics principles on how a building performs. And he worked at the Norwich University and he ran the facilities there and he did the energy management. So he wanted to use a material that had low embodied carbon and low embodied energy from an ethical company. And he found Ecococon at Future Build or Eco Build at the time in 2016. They then had the opportunity to go out to Ecococon in Lithuania as a customer of Strawworks, which was an organisation then that was managing design and build of straw projects. And they went out with the license holders of all the countries and had sort of a 3-day training. That's my dad at the back with the clipboard thinking. And that's my mum there just getting involved with the straw. So Strawworks and B. Rowan helped my parents go out there. They helped install the panels on site. They led the team alongside my dad. There was about 5 guys that helped build our house. They were, yes, they'd worked with straw before, but I want to stress with these panels that you don't have to have worked with straw before. You have to be able to read your drawings, follow instruction, use a level, use basic tools and concentrate sort of on what you're doing. A good carpenter skills. You don't have to be a straw builder to build with this. The only association really that's helpful is you understand about it being a high risk maybe for when it's raining and in like ensuring that it's dry in construction. But other than that, you don't need to. So we had loads of other trades along the way, which was great, made loads of lovely community and friends. And sadly, Dad passed away in 2020, but we did get him in the house almost finished. And he was really impressed by what we'd managed to rally. So that is, yeah, really nice. And that's just him having a beer in the sun because it's sunny today. So why not? So a little bit of background about Ecococon. I know we've got George on the call today, so if you have any more technical questions, like drop them in the chat and he'll, I'm sure, help answer them. So it's a compressed straw panel, multi-directional compression straw panel. It's effectively straw in a box, and it has a breather membrane that goes around the outside of it, and it has wood fibre. And you can have internal finishes. That clay is primarily the internal finish, and then the external can be ventilated facade or it can be rendered. It's a flat 400 wide panel. Passive House certified, REI 120 fire, and it's also I think they've achieved their silver for cradle to cradle, which is amazing. A shout out to George's house. So he also has built an Ecococon house called Old Holloway. You may well have heard of it. On the Passive House Trust website, it is Passive House certified. Again, a fabulous project demonstrating exactly what we should be building with. So just a shout out there. If you go onto Ecococon's website, there is tons of technical information that's really helpful, and also general just advice. It's a very good website with a lot of information. So I've just taken a screenshot here from their brochure just to show you the build up of the wall. And you can see the ventilated cladding or render, the clay plaster, etc. So their website is full of information. It has all woofy calculations. Just go and have a look. I did add in about fire because I think from working with SBUK, and often I get asked by architects and things when they come and visit our house that there's a risk of fire. So go and read the fire reports that Ecococon have done. They have an REI of 120. So yeah, there's a huge report. Go and have a look. It's not it's not a concern to us. I'm just putting that out there as a family. So when we went to Ecococon for the design, you sort of create this panel project of what you want, and we designed it in house with them. All the panels are load bearing, and at the point where my parents had the design done, they also were doing the roof elements. I think that is also changed now, but originally that was part of it. You can see the panels individually there, and you can see the lintels around doors and windows. They have the additional timber for structural rigidity. So we started the build in, I think, 2016-17. This is the slab. So it is a highly insulated slab. My parents, my dad particularly, didn't want to use concrete. But when it came down to the choices and costs and where you're going to put it, then he did put some in the ground. So we've a highly insulated slab with a screed on top. The actual walls that the panels sit on are an insulated, thermally broken cavity wall. I think I've got a pic, yeah, here. So they're 400 wide, filled with glape or foam glass aggregate in the middle. The internal leaf brick is a thermal block, and then the internal face of the external leaf is also thermally broken. So you've really stopped that thermal bridge through the brick plinth, which is, as we know, problematic on buildings. And I've stuck my thermal camera, imaging camera around the building, and we don't have any bridges at that bit. So I think he did do well. We had an external groundwork company come in and do this and pour the initial screed over the insulation. But my dad put all the stud work, little ladders for the panels, and he was out there the day before the panels were arriving, making sure that everything was completely level, which it was, and the groundworks team did a really good job, which was great. So all the panels arrived on 2 lorries from Lithuania. We had all the membranes, tapes, the rigid wood fibre and the clay and the roof I-beams. They all arrived, and they were stacked like Tetris, where they all came off in the right order as to what was needed on site. So very organised. Some pictures of just the beauty of them. They are just possibly one of the most beautiful building products that I've seen and that I get to be around. This is the west gable end. So the whole lot took about 2 days to unload and 2 days to go up with about 5 guys. But I will stress, they did know what they were doing in terms of Ecococon. So it would take longer, obviously, if you didn't. But it's, as I said, the technical guidance and advice for construction is exemplary, and it isn't rocket science. It's following the instructions, follow the order, make sure you fix things properly. So just more of the panels, just because it's a shame almost that they're covered up now. So we had a couple of things in this picture. So you can see the black plastic that doesn't stay there. That purely was put up for construction protection, just in case it had rain. I mean, this was in the summer, put up in the summer, but we do have rain in August occasionally. Less so here now. It's becoming much hotter. So just as it was going up, they were just getting those battens and getting that black plastic on just to ensure that it was safe. The actual timber in the middle that you can see, the oak frame, isn't necessary at all. The panels are load bearing. My dad wanted to put it in as a feature, so fair play to the man. That's what he wanted to do, and the roof calculation was then done with that in mind. But as I said, it's not necessary. So now you can see that there's something on the roof covering. So it's just an external wood fibre board that goes over the top of the rafters. The eye joist in the roof were filled with warm cell, cellulose insulation, and there's a membrane, and then there's a wood fibre board and a clay internal finish. As you can see, we've got some windows in, maybe, oh no, it's just the membrane over the windows, no windows yet. So externally is a breather membrane with ply strips which fix the breather membrane through to the panels themselves. The wood fibre is going to wrap all around this, and it is secured with thermally broken fixings. Some of the windows are going in with the breather membranes taped to the windows, and then to ensure that you've got the air tightness or the wind tightness. So you can see then the 60mm rigid wood fibre board's gone on. They've had the waterproof taping around the windows, all those thermally broken fissure fixings as well. Just assuming that there's no trying to stop the thermal bridging, which is good. So services, I am no way a services engineer, so I'm just going to take you through briefly the sort of what's happening in the building. So it was designed with PHPP as a passive house. We didn't get it certified, which just wasn't the motivation of my dad. I kind of a double-edged sword with that. I wish that he had, because I think the more buildings that we have built with sensible materials that prove they work, the more powerful they are. And sadly, I think in our industry, biobased materials have to fight 50% harder than mainstream materials, even though mainstream buildings don't perform. So I'm on double-edged sword. I understand the reasoning behind it, but I kind of wish that another one, would just be brilliant. So it has MVHR, which is great. We have a Zenda Comfy Q Air unit, which is brilliant. I change the filters up there every 6 months or so. You can really see the dirt and grime that comes out of those filters. We do live in a rural area. There is farms around us, so there would be a lot of particulates. So, but you can really see it. We have a thermal heat store we call the Dalek, that's slightly oversized, but my parents, it was one of the ones that was available, and my dad needed to get it in to the building. So we have hot water that is generated from the sun. So we have solar thermal, and we have hot water generated from a gasification back boiling stove, which I'll show you in a minute. So we have a couple of times in the year where it would be really good to have a wind turbine to generate hot water. And we end up putting the fire on even maybe when we don't need the heat in the building, but it's a very efficient stove, so it lets out minimal heat. It's very clever in what it does. So we do have an underfloor heating system, purely because it was put in because it can't be retrofitted in. So my parents were of the consideration that, well, if it did get to -30, then we'd need some heating, therefore we better put something in. And occasionally we use it, very occasionally. We're glad it's there. It's a good thing. And this is our amazing piece of kit. This is a wall therm, and it is just the most amazing piece of kit. So it's a fire with a back boiler on the back it moves the water, cold water comes in, it heats the water, and the water goes up and it gets stored in the heat store. But what's so clever is it burns so efficiently. It takes about 8 to 10 logs to heat the 1,000 litres up in the heat store. So when you put the logs in and it gets to a certain temperature, you flick up a lever, and all the gases that were waste that were going up the flue get pushed down and get reburnt, so that we're using the energy from those waste gases. So what comes out is really minimal waste and really minimal particulates. So it's absolutely brilliant. It doesn't let out a huge amount of wattage into the room, which is a good thing, because the house is so airtight and insulated anyway that you would probably overheat. But some of our pipes maybe aren't as insulated as they should be, etc., because it was a self-build. And now knowing what I know, maybe I'd be going back and redoing those. So there is a little bit of dissipated heat from the actual domestic hot water pipes, which we do see in passive houses when it comes to like overheating and stuff like that. So, but it's a fabulous system. And it's just, yeah, it's brilliant, very efficient. So yeah, as I said, we have solar thermal, which also is incredibly efficient. And then we also have a 20-panel PV array that's on the roof of one of the workshop buildings as well, and battery storage. So it's very techy science house. So this is just to show you the screed that went down and the clay plaster. You can see the base coat internal clay plaster has gone down. And also there's electric conduits that have been sort of cut through, and then they're plastered behind. You can just see over in the back there with the sort of white splodges. Wood fibre board over the roof, sarking board and cedar shingles with batten and counter batten. These have now changed, aged in colour, which looks really pretty. And the external building is also lime rendered. So clay plaster, just to sort of give you an idea of the air tightness. is an absolute joy to use. If you've ever had the opportunity to use it, then excellent. If you haven't, then try and get some. It's just the most amazing material. It's just so safe. So you can see my niece actually putting on the base coat with her hands. She must have been about 2. We just smush it into the straw, and then the top coat you'd use more of your trowels and your standard plastering tools. But we rallied in the troops to get this done, because this is when the diagnosis sort of stage happened with my dad, and it was a call in the troops moment. But it was an absolute joy. This is where my interest in clay plastering started from as well, which is nice. So internal colours, just to show you. So all the clay came with Ecococon on the lorries. The branding, I think it's Yuku, the clay plaster. They've I think there's other ones they've added in terms of colours and textures, but you'll have to check with George about that, because I'm not sure. But I just wanted to show you the colours. So there's blues, greys, yellows, greens, oranges, reds, pinks, greys, whites, and they're all natural. And you can we diluted them with the white to make different shades of colour. It's just, yeah, it's fabulous. And when the sun shines on the when it comes through the building and shines on the back of the wall, and all the mica in the clay just sparkles. It's just so beautiful. There's other things you can put in there as well, sort of dried flowers and stuff if you like, but we didn't. But again, it came on the lorry, and it's about 30 mil thick for air tightness. So we achieved 0.7 air changes. So this is what it looks like. So we've got quite a lot of glazing on the south face, and the west end where the conservatory is. The conservatory actually acts as a bit of a buffer zone, which sort of will definitely help the building to not become too hot, because we have no shading around us. We don't overheat. We do have summer bypass in our MVHR, and we do open the windows at night to allow like dual access night cooling. But we also, the amount of mass in the building and the fact that it's airtight, we just close the windows, shut it down. In the year, a couple of years ago, it was really hot here. I think we had like 36 degrees, 37. It was about 25 in there, and we had 5 people and 2 dogs and babies for a week and a half, and it just didn't get above that. So there's, thermal mass has a huge part to play. The floor is concrete. There's pallets on the floor. The clay adds mass. The straw has a mass to a certain degree. The wood fibre has a mass. So I think that's really helps its performance, but it's a very thermally comfortable building. So monitoring. Why? So you may or may not know that we have some of the worst performing buildings in Europe, and there was a report that was done that effectively rendered the current existing housing stock not fit for purpose. Which means we've got a lot of work on our hands to do with retrofit. But what's more concerning is we're still building the buildings that are not performing. So that's maybe more of a moral issue there. So we know that the energy efficiency of these buildings will need to be improved to meet the impacts of climate change, to meet targets by 2050. And so what we need to do more of is actually more monitoring and evaluating the buildings that are working, and why the buildings that are not working, and then what we can do that is the most cost effective, sensible practice to do, and what materials we should use, etc. So using science modeling and measuring in situ is vital to understand how buildings are performing. But this is not mandatory in the UK. They've brought out a British standard in 22 that is aiming to try and put more evaluation in as mandatory, but it's not. And a lot of the time, as I've said at the beginning, there is this performance gap. There's like a 60% performance gap where buildings are meant to perform to level A and they perform to level D, like 60% worse than they should. So yeah, we need to do more of this measuring. It needs to be made mandatory. So this is what my dissertation focused on, primarily also because I could find very little studies of in situ straw and straw panel houses, and I knew that it worked because we live in it. So it was a case of trying to prove that it worked, which is sort of the motivation behind it. So when it comes to doing buildings performance evaluation, there's different metrics you can use. This is a great paper. I think I've put the reference on a couple of slides to give you an introduction to building performance evaluation if it's something that you're interested in. So there's building fabric thermal performance things like air tightness, heat loss, the thermal transmittance, which is the U value, and then measuring moisture. There's also service analysis, energy performance, energy end use, and then indoor environments. There's all different categories that you can investigate when it comes to doing building performance evaluation. I chose these two, which is the U value and then the indoor environment, primarily because I managed to get hold of some equipment for free, which was great. So I contacted the Cambridge Architectural Research Institute. I'm based in Suffolk. And I went to meet Jason Palmer, who's done some work for Bays doing lots of U value measuring. And I said to him, I want to measure a straw house. Will you help me? And so he gave me the kit to use, which was just the most amazing thing. and showed me briefly how to use it, and then and helped slightly on like the error analysis and that sort of thing to help make sure that I knew what I was doing. Because I'm a complete novice in this. I've never done any BP before. I also need to shout out my supervisor, John Butler, who was epic, as we all know if you know him. He was so helpful to understanding the British standards and, well, yeah. So, but these guys lent me the kit. So I was like, right, well, I'll measure U values. And one of my sort of reasons to do this was because lots of papers show how over insulated buildings actually underperform. And this paper, which is a bit controversial because no science is perfect, and the way that you do analysis and statistical analysis can vary, but this is a paper that was using the same method as me, and they measured lots of highly insulated buildings, and they found that 93 to more or higher even underperformed compared to what they were meant to with their U value. So therefore the U value was higher than it should be, which I think brings up like further questions, which we'll get to later. So I put this in because this is it's highlighting measuring the actual in situ performance pardon me, situ improving the sort of understanding of how these buildings actually work to therefore try and improve the actual building standards and policy. So useful. These are the literature, some of the just things I think if you're interested in BP that you might be worth having a look at. So Gupta and Greg is a really good review, and then Fionn Stevenson's book is also excellent. And then, as I said, there's the new standard. So what did I monitor and measure? So I measured the heat flux through the wall on the north side of the wall using the kit that I'd borrowed. That then allowed me to calculate the U value of the wall, which is the overall heat that's transmitted through an area of the building per temperature difference Kelvin on each side of the wall. I also measured the internal temperatures and humidities of various rooms and outside as well. And then I could also, because I'd collected the heat flux data and the temperature data, be able to work out the R value of the straw panels as well. This is the British standard that I use, which is ISO 9869. The heat flow meter method. A couple of reasons why I used this. I could get hold of the equipment, but the motivation behind that was because it's the most widely internationally recognized non-invasive method. So it is far from perfect. There are a few methods you can use. And obviously now we have things like the pulse test. We have other things that Build Test Solutions also do. But in terms of British standards, this is the one that is the go-to. So I thought, well, if I'm going to be able to do this accurately and get the data correct, I want it to be comparable to as many things as possible. So therefore, let's try and do the most popular method. So this is also why I used it. So it basically measures the heat flux across a building element using heat flux plates. I'll show you a picture in a minute. Hoops flux, if you've heard of them, and then data loggers and surface temperatures. So I installed equipment on the internal face of the north wall to avoid any solar gain. And I effectively logged that, well, the data logger collected that heat flux data for 25 days over January 2024. This was to try to reduce the risk of small temperature difference. So when you read the British Standard, although it's not fun reading, but if you do want some reading of the British Standard, they really recommend that you have a temperature difference minimum of 10 degrees from inside to out minimum, and highly insulated buildings really should be a bit higher than that. And typically you would do this over 7 days. So to try and make the data more accurate, I did it over 3 weeks, because I thought, right, well, if I'm doing it over a longer period of time, those averages there will maybe be more accurate because I've got more data to collect, etc. So that was one way to try and reduce that. I did actually get the temperature difference needed anyway, so that's made the results much more robust. So I've just stuck those red pads on the walls, and I actually just stuck them on there with tape. They've got like a plastic little square around them, and you fix the plastic to the wall. And this was because that's what they did in the Bayes paper that Jason Palmer from Cambridge had used. This is far from ideal, and one of the things I think that would be really worth looking at for being able to measure wall buildings that are using clay plaster. So I collected data every 10 minutes for over a 3-week period. I did 4 days for acclimatization. I also stuck on the outside of the building an air temperature and humidity measuring. I did not do a surface temperature on the outside because I didn't want to, you have to dig it into the render, and I didn't want to make a hole in the render. So I did air temperature outside and internal temperature inside with thermocouples on the surface of the wall. So I put tiny tags all over the place, upstairs and downstairs, to monitor temperature and to monitor humidity, and also the weather station outside. I also was very fortunate enough to be able to borrow about 10 of these from Cambridge. So the maths, this is how the R value and U value were calculated. This is just using maths in the standard. actually quite simple. It's to do with looking at your heat flux and then dividing it by your temperature difference, and then the R value is the other way. So it's actually not too difficult. It was just about getting the right average, making sure the data I'd collect it was accurately reported and stored in my Excel sheets. And then the most challenging thing was actually trying to work out the error calculation. Because the British Standard is just abysmal to read. It is. I remember having a meeting with John, and we sat there for an hour scratching our heads on how on earth we could understand what it was saying, which I think makes me think that all these methods have inaccuracies, but probably because the British Standard is so hard to understand that obviously there's going to be inaccuracies. I think someone needs to translate them into a way that makes it accessible for people to understand. So we eventually managed to work it out by using other papers, which was probably one of my proudest achievements in terms of this whole dissertation, was to work that error out at 13%, which just, yeah, was a mountain, shall we say, but we got there in the end. So results. So the designed value of this build up from Ecococon is 0.13 as a U value, so watts per meter squared Kelvin. And then what I measured was 0.148, so you could round it to 0.15. So we were pretty chuffed with this, to be completely honest, for a measured in situ U value. But then what was even more exciting was when I put my error value on, it actually could have been within the range of 0.13, which means that the building, to a point, could be performing exactly how it would be in a laboratory. Now, obviously with errors, human error, installation of equipment, all that sort of thing, not being a BP expert, you're obviously going to have an error range there. But as a family, I think my dad would just be so chuffed. We know it's performing because we live in it, but to have that data is just really cool. So the R value as well was really close to manufacturer. The higher, it means it's more insulating. So an R value is a thermal resistance value. So if it resists more heat, then it's more insulating. So again, similar, in line with Ecococon as well, which is great because it's a lived-in building. So we were really happy with this. So the heat flux, these are things that sort of are errors or limitations within that method. That little red heat flux plate is actually only measuring a tiny area of the building. It can't predict the overall performance of every aspect of the building fabric. It's representative, and that's how it's accepted in the science sort of world. It's a representative sample. Now, you could have done loads of them, which would have been another way of doing it, which I didn't do. It does also have high dependence on correct calibration, humidity, and then sensor to wall attachment, as I mentioned earlier, to the clay, and the sufficient temperature gradient, which we did actually meet. Surface temperatures are also more accurate than air. And outside, I didn't want to make a hole in the render, so it is air outside. But I calculated that into my error calculation. So all of these things have been factored in for. So I tried to reduce the risks that I've just mentioned by extending the days, as I've said before. Larger data set averages out fluctuations, reduces the risk of invalid results. I did also calibrate the equipment as per the Cambridge instructions, and the error calibration, the error calculation, included that I hadn't calibrated it anyway. So I went passive house over the top in terms of ensuring over error analysis rather than under error analysis, partly because that's more, for me, that just felt better. And also during the measuring time, I did actually manage to have the temperature difference that was required in the standard, which was so exciting, which you would expect to have actually because it was winter and our house is very insulated and warm. But it's reassuring. So therefore, that in situ U value that I measured from the study is creating the assumption that somewhere between those two values is what was the heat that was lost through my wall in January 24. So it's within the manufacturer's range, but also is a range that we're really happy with, that I think shows that it's working. Things that have impacted my U value, as I've said, in terms of the adhesion to the clay, which is the second point of the heat flux pad, the rougher surfaces, that we need some more studies to work out what is the best thing to stick that with. And also just if they're not placed correctly. I think they were placed correctly, but again, it would be worth reviewing. And then also just having more heat flux pads. So I did actually have a couple of kits, but they only used 2 in that place. And then the other one I used for some reason didn't do anything that it was supposed to do, and has now gone back to Cambridge. So I think that would really help if I'd done multiple as well. So this is a paper about straw performance, straw bale, and you can see the red line is the data from my study using only 1 heat flux meter kit, and it sort of fits actually in with this typical build-up of straw, even though it does have the wood fibre on the outside, which is reassuring to me that it fits in with other trends that have been measured in situ. These are bale buildings, though, must stress they're not panels. So I also measured internal and external temperatures. The average external temperature was 3.6 degrees, internal range from 20 to 21. There's also remembering here that the building is very airtight and has MVHR, so we would expect the temperatures to be stable and sort of consistent, which is great that then they were. That's exactly what they sort of were. Obviously, if you open doors and windows, it's going to change a bit. So in terms of heating the building, our building is mainly in the winter actually heated from the sun. So it's positioned to face south, and the sun comes in through the windows and hits the back wall and hits the slab on the floor and actually heats the mass. We don't light the gasification stove that much, but we do light it. And in this study here, when I reported how many times we lit it, it was about 50% of the time. But it also is for hot water. If there isn't the sun, then we need the hot water. So we do have an iBoost that's on the thermal store upstairs, so we can take electricity from the grid and change it into hot water, power the heat store to heat up. But it's more electricity expensive doing that, so we'd prefer to do it with the fire because we have logs. So we might be lighting it more from that respect. I think it also highlights the power of internal gains in buildings. So if you live in a low energy building or an airtight building that's insulated, you'll be really well aware of this. But if you're cooking of an evening and you've got pets and there's a couple of people there, the building really drastically increases in temperature in those moments where your internal gains are larger. And then because your building is warm and airtight, those internal gains stick around. So it shouldn't be a way to heat a building. You should always have a backup with an actual heating system. But I think it's a really important question to look at in terms of a way to heat your building. I think there is a discussion there to be had, as well as obviously the solar gain, as long as there's sun, of course, which actually a couple of days there really wasn't. So yeah, therefore very stable internal conditions, regardless really of how we heat the building. They were all very stable and very consistent throughout the whole time. Relative humidity, so roughly around the 45% on average, outside 70 to 80%, significant difference between them. And we would expect this. We've got MVHR going on, which is helping. But I think that what's really nice is that we know, we've probably seen this picture before, but this shows you sort of the gauge of relative humidity where pathogens like to breed and reproduce. So you really want your building to be within the range of 40 to 60% humidity. Some people find 40 is a bit low, so around the 50% mark. I mean, most buildings in the UK are in the 70s and 80s constantly, even with extracting bathrooms. So I think it's a really underlooked thing in health and indoor air quality. It's also a really good measure to associate with things like carbon dioxide levels and VOCs and stuff. So if you have high relative humidity, you're probably having high levels of those things. So it's a really good measure of a rough measure of that. So our house is doing really well. We're in this safe zone during the 25 days. We do know we have MVHR, as I said, and also the materials are hygroscopic. So the clay plaster will absorb and release moisture or water vapor when levels are higher and when they're not. It's an incredibly hygroscopic material, and so is the straw, and so is the wood fibre. So you've got materials in there. I think it would be really interesting to do a study where we turn off the MVHR and we measure the moisture levels in the clay, and we see what happens over a heating season in terms of moisture. I think that would be really interesting. So yeah, you get this lovely moisture buffering, which is a brilliant thing that effectively most natural materials, if not all of them, do. They all have hygroscopic qualities. Occupant survey. So sort of the last aspect of the BPE is that it really must include occupant surveys. And this is because buildings perform relevant to how the occupant live in them and use them. So to make generic data and generic sort of methods doesn't really work if you don't then do a questionnaire to see who opened what window and what did that and where did they dry their washing and how many times do they have a shower a week and how do they use the space. So I did a survey, but obviously it's very biased because we live in the house, so we have got a bit of the biases in there. Although when we have visitors here, they all share similar feelings. Everybody comments on the acoustic properties because it's very acoustically pleasing would be the best. It's not silent, but it's very soft sound. which is lovely, and thermally it's really comfortable. So we do, when people come and stay, they do say it feels a certain way, which I think is actually really common in when you go to a lot of bio-based material buildings, whether it's wood fibre in a timber stud, a hempcrete, or straw. You get this general feeling of like a sort of warm hug. So this table just summarises sort of some of the things I've talked to you about, so we won't stay too long on it. I just put it in here because I spoke at Future Build a couple of years ago initially before I'd done any research, and I've just added stuff on. But it was just talking here really about the carbon. So there's about 20 tons of carbon just stored in our panels, but obviously with all the timber and everything, I think it would be interesting maybe to talk to John and do some more carbon analysis on the building itself. And I've just highlighted the overheating, the idea that there's mass in the building to reduce the risk of overheating is really important and really underused and understood and should have a more prominent place. And it also just gives you an approximate cost for the build, as it was a self build. So back to this paper that I mentioned at the beginning, where I said about how highly insulated buildings were underperforming. And even if you could even look at our data and say, well, it's not performed at 0.13, Annie, therefore it's underperforming. I mean, yeah, if you were looking at just the U value, I suppose you could say that. Obviously, with the error analysis, it sort of argues back a bit on that point. But I think this is a really valid point that we need to address, that if we're building buildings that are highly insulated, but they're made of high embodied carbon and high embodied energy materials, but they're still not performing, what was the point? When actually we could have been insulating them with something that stores biogenic carbon, using the building as a carbon sink. And yeah, fine, maybe it underperforms slightly, but the benefits, i.e. carbon capture, indoor air quality, hygroscopic, buffering, all of those things you get just because it's a natural material. You just get it for free because that's what they do. So at least if we did it like that, then you'd be getting a better health of a building with the occupant in there with lower embodied carbon and lower embodied energy. But yeah, fine, maybe it isn't to 0.13. So I think this is it's interesting discussion, but I think also like things like airtightness make a massive difference when it comes to retention of heat. I think they're massively underlooked and needs to be more at the forefront, which is why I love what Ecological do, because we do CPDs all the time in it, trying just to spread the awareness of the importance of a warm building. But then obviously you need to look at your ventilation strategies as well. So sort of last bit I want to just talk about briefly is about the carbon and about highlighting the importance of looking at the whole life carbon of a building. Now, we had the Future Home Standard consultation, and when I read through sort of what the built environment professionals had said, 99% of people were raising embodied carbon as something that should be in a metric somewhere. As we make our buildings more efficient with operational carbon, then we need to look at our embodied carbon and look at that balance. And I think I'm just sort of flagging that. But I think, and hopefully that's coming. But obviously, bio-based materials with low processing would hopefully be great in that respect. So John did some calcs for me for Future Build a couple of years ago, and I just think they're really nice to share. So he did this graph here that shows whole life carbon emissions per 100 metre square of different walls to the same thermal performance. And as you can see, masonry has 3.4 times the emissions of the straw and eye joist and 2.1 times that of Ecococon. But yet we are building all the buildings with masonry and they're not performing and emitting, which is madness to me. And then obviously masonry was never going to win on this category, but we're just putting it in because we're SBUK, and I think it's just highlights again another amazing thing about biogenic materials. They're going to store carbon because they photosynthesize. So obviously the straw is going to store 100% more carbon dioxide than the masonry. The masonry wasn't going to stand a chance there. So yeah, that sort of brings me to the end of my talk with you guys. And throughout doing my dissertation, there was a lot of reflections happening in the wider aspect of the practical construction industry alongside the actual academic, and the disparity between academia and practical in trying to drive forward change. And I think, we can't deny that we're in a climate emergency, and our built environment, it needs to be better. It needs to do better. And it isn't that we don't have solutions. We have solutions. We have so many products that should be more in mainstream, and they're not. And there are still some barriers there, but a lot of the barriers have been addressed. So I think, we need to do better. We know that passive house design is good. It's a good design method. It's rigorous. With the certification, it's even better. But even if it's a low energy version of that and it's not as certified, it's brilliant. But what I would call is that if we're doing the low energy buildings, why are we not then trying to do them with bio-based materials as well, rather than doing them with high embodied carbon and high embodied energy materials? That's not to say that all natural materials do have low embodied carbon. Some processing doesn't, but I think it's a balance of get the right material and the low energy design. I know that straw panels perform well thermally and they sequester carbon. Therefore, can we use bio-based buildings as carbon sinks? Obviously, we'd have a huge amount of carbon we'd have to trap in order for it to balance as a proper carbon sink. But if we don't do it, then we've lost that opportunity. So it isn't saying that just building bio-based buildings would be solving climate change, but it definitely would be a helpful thing to do. And I just think the last point is that bio-based materials should be in mainstream construction. They should be in education for mainstream construction. Young people coming up into construction, colleges should have exposure to them. They should know what wood fibre is and how to install it. They should understand about airtightness. They should understand about biogenic carbon in materials, how to care for bio-based materials. So there's a lot of education that needs to happen, that stuff is starting to happen, which is amazing. But I think there's just no excuse really. Bio-based should be above ground in the places where it can be, and we leave the other stuff that needs to be in the ground for strength and structure to stay in the ground. And yeah, that's just a picture of my dad in the sun with his beer, because it's a sunny day, and he would love to have talked you through all this today and been part of it. So thank you so much for listening. Over to you, Cyprian.
Thank you, Annie. That was absolutely fantastic. My goodness, a whistle-stop tour.
Yeah, sorry, it was a lot of information.
No, don't apologise. Don't apologise. Seriously. I know where you live now, so I'm going to come and move in.
Yes, come and join.
We're all going to move in.
Come and move in.
Right. Hands up, who's going to Annie's? No, Annie, that was absolutely fantastic. Thank you very much for that.
Thank you.
The depth of which you went to in breaking all of that down, from the conception to the final outputs, and the evaluations, everything was just on point, absolutely on point. And we've had so many questions.
It's been a labour of love.
I bet.
Yeah.
I mean, well, one of the things I wanted to ask before we get on to any more questions, I'm mindful of time. We've got a few minutes left. Was timing. I mean, please don't go back to the slides.
Yeah.
Just if you can recall, you said 2 days to load.
Unload, yeah, about 2 to 3 days to put up. So the whole structure was delivered and up within a week.
Right. And
the roof then came 2 weeks later. It was a bit delayed. Some part of the roof, like the wood fibre, there's something on another lorry that arrived. So it would have been probably 2 weeks, the whole thing, if it hadn't had the week in between. But I think it was 3 weeks in total or something.
Okay. And that was delivered with people who were up to speed with Ecococon products?
Yes, organised through B. Rowan at Strawworks. There was a team of guys. So when my parents went out to Lithuania with B, they met some of the guys there, because the people that went to that sort of event were the people in different countries that were recommending Ecococon and building with it. So there was contractors there. So I think some of them were there, and then others were just carpenters that she knew in her network of natural building that came. I think so. There was 4 here all the time and 5 sometimes. Okay. Well, over that week and a half or whatever, 2 weeks, over the 2-week period.
Right. And I don't know if George wants to come in with this. Is this a service that Ecococon provide as part of their overall package? So,
not that I don't think so.
Right. Okay.
Not that I'm not aware of, but George can, go for it, George.
Just generally speaking, the beauty of working with prefabricated materials is that it's the ease with which you can construct with it enables anyone who has just, I suppose, the most simplistic experience in carpentry to deliver without too many obstacles to overcome. And one other question I wanted to ask was regarding the services. So the underfloor heating, I think you, correct me if I'm wrong, but
no, go for it.
But I think you said your family decided to install it as an additional
sort of yeah. It was, I mean, it's sensible to have a way to heat your building, and they didn't want a heat pump So they thought, right, well, what's the most sensible way of doing this? Well, put it in the mass of the floor, because then what if it did get cold and you spent 3 days heating that underfloor heating, it's going to keep the heat.
Yeah.
So then you don't really need to put any more in, or very little, to heat it, and it covers a big area. And then once that mass is warm, it's just doing you a massive favor. So it's a really efficient way, because it's so airtight and insulated, the floor, and so is the building, that heat isn't going to escape. So that was just sort of it went in as a, I remember them having the conversations about it. My parents being like, "Is it going to get to -30?" And don't even know what it's going to be. But actually, no, we're really glad it's gone in, because you couldn't put it in. You couldn't retrofit, and it was a tiny cost in the grand. Like that thing was a tiny cost in the grand scheme of things. It was well
Mm,
worth it.
mm.
But yeah, choices.
And
There are so many choices now people can make as well. There's more technology on the market now than there was when they did it. There are loads of services stuff that I would not even know where to go into.
yes,
So,
yes. I think there was also, I think the penultimate slide, where you were talking about the effects of working or building with bio-based materials means that there's less harm to the planet. One of the thoughts I had, and maybe you might be able to chip in with this, I'm uncertain, but it's supposing, and I would never ever want to put this idea, I suppose I'm doing it by just asking it, but supposing you had to demolish the home, it means that whatever it is that is going into the ground is considerably less harmful than what a typical house of that size would be, right?
I mean, yeah, arguably it could potentially, yes. I suppose it would be quite good to do some maths on that. But I think the other thing is that ideally we want to build buildings and leave them.
Yes.
Like, don't we? Like, we want to leave them, build them well, and let them last 200 years, like we used to build buildings. Why are we taking them down?
Yeah.
Like,
Yeah.
why are we taking? But if you did want to take them down, they're panels. In theory, yes, why not? But
Yeah.
I suppose you could argue that you could take bricks down, clean the mortar off, or use it as hardcore. I suppose all of them have arguments on reuse potentially. But yes, you're right. Like, in theory, yes, that's one argument. I'm more of the advocate of leave the building, build a good building, and leave it, and it will just serve future generations, and maintain it. I think make sure you know
Yeah.
how to maintain it and check your services. That's one thing about having buildings with more of this technology in them. People need to be trained in how to do that. And buildings should come with a manual, so you know how to do your MVHR. Do you know how to service your solar thermal? Do you know what a heat store is? What might be an issue? What's the pressure valve? That is a desperate need in the market for. So, and I think actually that is coming, like material passports, building passports, those sort of
Yes.
things. But it's so important to a low energy building, particularly with overheating as well, like curtain shutting, open the windows, that sort of thing. And there are challenges with that. We're very fortunate, and I'm very aware that we're very spoiled, because we have this detached house in this beautiful plot that is not realistic to, loads of other houses. It's a bit of a glorified eco home. It's a Christmas tree. It's a Christmas tree, but it's beautiful and I love it. But yes, it's, yeah.
George, can you hear us, and are you able to talk? No,
We can't hear you,
we
but we
can't
can
hear
see your
you.
mouth
Never
moving.
mind. I'm so sorry. But look, I suppose this is a great time to plug it, because if you go back into our YouTube channel, you will see the previous talk that we had George on, doing almost exactly the same thing as Annie has delivered today. Fantastic talk on his own home called the Old Holloway. He was the first person to have Ecococon panels built on a family home in this country, and he was like a guinea pig, I suppose, much like you were and are. Annie,
Family of guinea pigs.
are you still uh, con, compiling data for the home?
No, I mean, I haven't. I've stopped now just purely because of capacity. I just don't, I don't have any time. But I have actually, when I spoke to Cambridge, I sent them all my data and the dissertation. They just said to me, look, you keep that kit and use it. If you want to remodel it, you keep it for the next. So yes, I would like to now set up the other heat flux on one wall, redo it. Let's see, but it needs to be heating season, so it will be next winter. But I'd like to do other bio-based buildings too, like some of the hempcrete buildings we've built as well, because I think that any of this data is just
Yeah,
invaluable.
yeah. There are a couple of questions that I'm going to put out, and that I think perhaps some of the most common questions. John Dalton has asked, what cost per square meter did you pay for the house? Would you
Yeah, I
be
think it was a self-build, so it's hard to factor in all of like dad's labor hours,
Mhm.
but I think it came out between 1,600 and £2,000 per meter square.
Right.
But it's really hard. I tried when I did the costings for Future Build. I really tried to add in how many we tried to work out the time that had been finishing, because it was the finishing. It wasn't the panels. The panels went up really quickly, and the roof went on, but it was all the rest that we did ourselves. So it's really
Yeah.
hard to put a. But that's sort of what we came to. It's around the £2,000 mark.
Okay. And there's another question about clay. I mean, I love so much that you're using bio-based materials throughout your home. What was special about the clay used for the internal wall coming with the kit? Was the option considered to use excavated foundation clay?
We didn't do that. You could well do that. I don't know what the policy is with Ecococon in terms of their package at the moment, but George will probably be able to type in the chat more if there's a I don't know if there's a rule that you have to use UQ clay now, George, or what the system is. I think that my parents bought the whole system, but I don't know. Yeah, he'll have to answer whether or not that is expected. But you could you could put any clay plaster on. You could put lime plaster. You could put any breathable plaster. You could technically put a membrane in a surface cavity. You could, in theory. It's just, why would you want to? You want to put that clay on to help control the indoor environment of the building. But absolutely, you could dig the foundations and make your own mix. I think if you were doing that, you could then add the chopped straw, so if instead of using a mesh, you could do a base coat with chopped straw in there, so then you are reducing the need to use plastic meshes, and then top coat
Yeah.
a smoother clay. But yeah, it's just clay. It's just Estonian clay processed without the stones in it. They've done that work for you, and it arrives in a big bag, and you basically wet it up with a mixer to the right consistency and slapped it on the wall. So you could use whatever clay you
Yeah.
like.
Gosh, Annie, we are so spoiled, very spoiled, and I'm really glad that George joined you on this call today
Yes,
because
thank you, George. I'm sure you've
both
been
he
adding
and
in
John,
lots of information,
both
lots
he
of
and
technical
John
stuff.
sorry,
Oh, good team.
both he and John are brilliant experts in this area, in this field. I think I'm going to bring it to a close now. It's a couple of minutes before the end. It's just to say that please do keep a date in your diary for the 25th to 26th of June. Coming up soon is the Straw Building UK Symposium. This theme will be on biophilia. So biophilia, we're working with nature, looking at how it is the built environment even is working around nature. And so we have a host of experts on those 2 days who will be talking. There'll be workshops. Please do keep an eye on our website. We're going to be publishing the details for that very soon in the coming week. So get your tickets whilst they're hot. Annie,
Yes,
thank you again. You
pleasure.
have been a star. I
Pleasure.
really, I can't thank you enough. I'm so
Pleasure.
glad.
Thanks for having me.
I'm so glad that you're on our board. You're part of the team.
Thank you.
That we brought you on, and your words. I'm lost for words.
We'll leave it at that and let everyone go and
Yes,
go back to work and have some lunch. Nice to see you all. Thanks for coming,
Lovely to
everybody.
see you all. Keep an eye on our website for further updates for new events happening and, of course, for the symposium. Thank you very much, George and John, for joining us today, and everyone on this call. This has been another Straw Building UK webinar. And thank you, Annie. Have a lovely day.